Oh, actually, very next slide. So this is another one of those cross sections where it's not showing erosion. This is showing what the folds would look like if they could complete with no erosion happening over millions of years. So you can see here the thrust faults and reverse faults, the folds, the suture zone, and this nappy, sections of crust that have been weakened, detachment zones, a lot going on in the Alps. Of course, the actual surface is different due to erosion and slumping. For example, this lobe could never actually stick out like that. It would either break and fall, or bend, or erode. But the point is that not all orogenies are the same. Sometimes we get something that's going to have much more thrust faulting. Sometimes we're going to have something that has more uplift, sometimes more folding. But also they get depicted differently. In this case, we're showing a hypothetical surface. Other times, some of the other cross sections, we've shown an actual land surface. So individual layers are incomplete because they've eroded. Here it's showing more complete layers, but a fictitious surface. The nappy is a large sheet of transported rock that has some recumbent folds in it. So that's folds laying on their sides. Like this fold right here is a recumbent fold. It's laying on its side at less than a 10-degree angle. And so this is rock that has been moved a long ways, transported rock, and it's a recumbent fold. Now, the Alps are pretty cool because being in Europe, they've been studied and mapped for a long time, and they studied them so much that the ancient maps of the Alps are some of the best maps from that time period. You look at maps of North America from 400 or 500 years ago, and it's kind of funny because they got so much wrong. Maps here, they got them really, really accurate. So accurate that I'm going to superimpose images from Google Earth on their map and watch what you can see. Incredibly accurate ancient maps. So this map, drawn a long time ago, if we did a topographic map today with our new satellite technology, it would be almost the same map. On the other hand, another way of looking at it is a geologic map. This is going to tell us the age of the rocks exposed. Very different than the topography or shape of the rocks. This is telling us the ages of the rocks. And you can see a general linear trend as the layers were folded and thrust upward. Sorry, I'm going to sore throat here. In this image, it's a little bit hard to see when it transferred into PowerPoint. I lost resolution, but you can see the different types of rock, and if you wanted to go ahead and study the Alps, you can download geologic maps and they'll look just like this, except you can read them. So crustal thickening and then extensional collapse are the next stages. So initially it thickens due to the shortening. As you push it in from the sides, it gets thicker because you can't destroy the material. It has to go somewhere. It gets squished upward and downward. This causes an increase in pressure and temperature, especially at depth. So lots of pressure in the middle here, lots of increased temperatures down here. That makes the rock weaker and softer. As you heat it, it's no longer as strong. It's no longer as rigid. The mountains cannot uplift indefinitely. They will collapse under their own weight. So eventually you start getting this kind of action. They're collapsing downward. We've got some thrust faults still there. We've got normal faults happening. We've got thrust faults out on the edges as the material slides outward. It's kind of like taking a large chunk of butter or cheese. When you take it out of the fridge and it's nice and cold, it'll hold its shape perfectly. Leave it out in the sun and it will soften and start collapsing under its own weight. You don't have to put anything on it, just its own bulk will cause it to collapse as it gets softer. And so you have spreading out to the sides. You can see this little dish that it's on, same size dish in both cases, at time 1 and time 2. But at time 2, the block is no longer as tall, but it is wider. And you get faulting. Same thing happens with the mountains. It's like currently the Himalayan mountains. They are as tall as they can get. Plus or minus a few meters at most. Between erosion that's occurring and their collapse under their own weight, it doesn't matter how fast India gets shoved into Asia, the Himalayas cannot get any taller. Delamination is another thing that can occur at one of these thickened zones much later. And again, this, as it says down in the bottom left, this is not to scale. This is just a very cartoony drawing of what can be going on. So we have some mountains, not shown here, but like the suture zone would be right in the middle. This is thickened crust. This is thickened lithosphere as a whole. And this is thickened because it used to be, it's like this lithosphere here, as it got compressed with something else, is what got pushed down. And so this was lithosphere that used to be up higher, cooler, that got shoved down into the mantle. Therefore, it's much cooler than the mantle. That makes it denser. It's cooler and denser, and it's sticking down like that. It can actually start to drop off. Its tensile strength is inadequate to keep that large lobe there. Chunks of it just drop off and sink down into the mantle. When that happens, warmer plastic mantle material slowly flows in, because again, we never create gaps. There are never empty chambers down there. At the same time as it's slowly breaking off, that mantle is slowly filling in. And so now the new bottom of the lithosphere is in contact with fresh hot mantle material. It causes melting to occur. That melting means magma, which is more buoyant and starts rising through any cracks that might exist. And there are plenty of cracks. This was a collision zone after all. And this rising can create new uplift. There's, you figure you take and you squish hot magma up into this area. There weren't any gaps for it. Even the cracks, they're closed. There's not an open gap. It's not like, there's a space between one chunk of rock and the next chunk of rock. There's just a fracture. The magma actually pushes that fracture apart, displacing the rock for that magma to rise. So you figure there's a lot of buoyancy. It's not just minor. There has to be a lot of buoyancy for that magma to push its way through and displace all of that rock and push it aside to rise through those cracks. That means there's enough buoyancy to actually uplift the land, which then starts slumping because it was already raised up. It was already a mountainous area. Uplift it more, and the upper parts of it collapse under its own weight. Especially if you're filling the roots of the mountain with hot magma, it's weakening it even further. One of the last things that I want to talk about is another consequence of collision, of what happens to the primary plate that's hit by the smaller plate. One plate is always larger than the other. So what's happening to that large one as the small one slams into it? We can simulate it on time scales that we can appreciate as humans and see what's going on by having a block of clay and a block of wood sitting on a table and slowly pressing that wood into the block of clay. Obviously the clay would have to be braced and you'd have to have an awful lot of force to jam a block of wood into a solid block of clay. But, set up the right experiment and you could do this in your own home if you wanted to. And you would see something like this happening. At time 2 it would start, you get cracks and faults forming in the clay. Keep pressing that wood in, and you would get a chunk of clay kind of splitting off, and then new faults and cracks forming behind it. Keep going, and another chunk is going to split off. We have some strike-slip faulting along the edge of the block here, and we have what's called lateral escape. We can see this in the real world right over here. India is like the block of wood. Asia is like the block of clay. As India slammed into Asia, it displaced crustal material over here. These lobes of clay are a good analog for these lobes of land that got displaced as India slammed into Asia. This is lateral escape. Another type of uplift we can get is plateau uplift. This can happen pretty far inland when we have subduction that's happening, the angle varies. This can happen based on the material of the mantle, the densities involved. There still has to be a part of the subducting plate at a steep enough angle to actually pull it down and pull this plate along, but segments of it can be fairly horizontal. This allows the plate to reach further inland. So, here we've got the Sierra Nevada mountains coast over here. Really far inland, we've got the Colorado Plateau. When the angle of the subduction changes again, we can get some more melting. That magma can rise up and inflate magma chambers, uplifting the land and creating a plateau. There are some other places in the world plateaus can be created in different ways, but this is one example for the Colorado Plateau because of subduction. And the last thing I want to talk about is crustal accretion. Remember I was saying that whenever you have some crust that's too buoyant, it has lower density than the mantle, it will not subduct. This can be continental crust. It can be volcanic islands out in the middle of the ocean. It can be microcontinents. It can be any crust that's not highly mafic. It will not be dense enough. It will not subduct. So here we have a cross-section of the Appalachian Mountains in the United States. On the inner continental side, we have a fold thrust belt and host continental material. So this side of the mountains is made up of stuff that was there, that was part of North America. In the middle of the mountains, we have a heavily metamorphosed zone made up of different kinds of, some continental rock, some accretionary prism material, some oceanic crust, some crust from the whatever came along next, so smashed together that it's metamorphosed, and that's the heart of the mountain. Then we have another Schutzer zone with some exotic terrain. What this is like maybe an island arc, maybe a microcontinent, maybe some segment of something that had been rifted off but was continental material. The point is that it's felsic, it could not subduct, but it wasn't the actual continent from the other side of the ocean that reached North America. So then there's another suture zone. And then another exotic terrain, in this case identified as a microcontinent. And then another suture zone. So, you can get island arcs and other land that will not subduct, but isn't truly part of a continent, that gets stuck on here and separated each time by a suture zone, because there was, after that island arc, was more oceanic crust. After that microcontinent was more oceanic crust. Before you finally get to land that was part of the continent from the other side of the ocean that subducted. So we have North American continent, other continent, and a bunch of other stuff that was between them that did not subduct and get stuck into that mountain chain. And that finishes the collision chapter, chapter 17.